Deep in the cosmic void between stars, something extraordinary defies everything we thought we knew about planets. Picture this. At this very moment, less than 5 light-years from Earth, a world the size of our own planet drifts silently through the interstellar darkness, its surface locked beneath miles of crystalline ice, yet harboring beneath that frozen shell an ocean deeper than any on Earth, warmed by the slow decay of radioactive elements in its core, and possibly teeming with alien life forms that have never seen sunlight. Recent groundbreaking discoveries suggest that these rogue planets may outnumber the very stars that light our night sky by 20 to 1, fundamentally reshaping our understanding of planetary formation and revealing that the universe may be far more alive than we ever dared imagine. The cosmos harbors secrets that challenge our most basic assumptions about where life can exist. When astronomers first began detecting these wayward worlds using a technique so precise it can spot the gravitational influence of a planet smaller than Earth from thousands of light years away, they discovered something that revolutionized our understanding of planetary systems. The galaxy appears to be absolutely teeming with planets that orbit no star, receive no warming light, and exist in perpetual cosmic winter, yet may be among the most habitable places in the universe. Through painstaking observations using gravitational microlensing over 9 years at the Mount John University Observatory in New Zealand, scientists have uncovered evidence that our Milky Way galaxy hosts an estimated 20 times more rogue planets than stars. A discovery so profound that it suggests planets may be the most abundant type of world in the cosmos. Gravitational microlensing works like a cosmic magnifying glass, relying on the precise alignment of a foreground rogue planet with a background star and Earth, causing the planet's gravity to bend and amplify the starlight in a characteristic pattern that lasts anywhere from hours to months. The technique is so sensitive that it can detect planets with masses as small as 1/10 that of Earth, floating freely in the darkness between stars, completely invisible to conventional telescopes, yet revealed by their gravitational signatures as they drift across our line of sight to distant stars. What makes this method extraordinary is that it doesn't depend on the planet emitting any light or heat of its own, allowing astronomers to discover worlds that would otherwise remain forever hidden in the cosmic dark. With approximately 100 billion stars in our galaxy, the revelation of 20 rogue planets for every star translates to a staggering 2 trillion rogue worlds drifting through the interstellar medium, each one a potential laboratory for exotic forms of life that have never experienced the warmth of a sun. The James Webb Space Telescope has revolutionized our ability to peer into this hidden population, discovering 6 new rogue worlds in stellar nurseries nearly 1,000 light-years from Earth, including binary pairs of rogue planets orbiting each other like cosmic dancers in the void. Even more intriguing, the Webb telescope recently observed a rogue planet designated CHA 1107-7626, undergoing unprecedented growth, devouring gas and dust at the record-breaking rate of 6.6 billion tons per second, suggesting that these worlds can continue evolving and accumulating mass even after being cast into the interstellar wilderness. The formation of these cosmic wanderers represents one of the most violent and chaotic processes in the universe, a celestial version of planetary billiards played out over millions of years during the turbulent birth of star systems. Computer simulations reveal that during the early stages of planetary system formation, when massive gas giants migrate inward through their birth disks, gravitational interactions create resonance chains that destabilize entire systems, flinging smaller worlds into the void at velocities exceeding the escape speed of their parent stars. The process begins innocuously enough. As giant planets spiral inward due to friction with the surrounding gas disk, they create gravitational resonances that overlap and drive chaotic diffusion, leading to planetary collisions, orbital crossings, and ultimately, the violent ejection of worlds into interstellar space. Current models suggest that smaller Earth-mass planets are preferentially ejected during these chaotic events, explaining why terrestrial rogue worlds appear to vastly outnumber gas giant rogues in the cosmic census. The ejection process is remarkably efficient, with simulations indicating that systems initially containing multiple planets are likely to eject more than one world on average, creating substantial populations of wandering planets for every stable planetary system that survives the violence of its early evolution. This cosmic reshuffling occurred throughout the galaxy's 13.8 billion year history, with each generation of planetary systems contributing to the ever-growing population of interstellar wanderers that now constitute the majority of all planets in the Milky Way. But not all rogue planets were born in traditional planetary systems, only to be later exiled through gravitational violence. Recent discoveries have revealed that some of these worlds may form through an entirely different and equally fascinating mechanism, collapsing directly from clouds of gas and dust, much like stars, but lacking sufficient mass to ignite the nuclear fusion that powers stellar cores. These objects represent the lowest mass outcomes of the star formation process, with masses ranging from just a few times that of Earth to several times that of Jupiter, times the mass of Jupiter, existing in a twilight realm between planets and failed stars. The James Webb Space Telescope has identified examples of such objects in the Orion Nebula, including surprising binary pairs of rogue planets orbiting each other like miniature stellar systems, suggesting that planet formation can occur even in the absence of a central star. This dual formation pathway explains the remarkable chemical diversity observed among rogue planets, creating two distinct populations with vastly different compositions and evolutionary histories. Those ejected from planetary systems retain the heavy element signatures typical of planets formed in stellar disks, rich in silicates, water ice, and organic compounds, while those formed through direct collapse from molecular clouds exhibit chemical fingerprints more similar to brown dwarfs and low-mass stars, with compositions dominated by hydrogen and helium. Advanced spectroscopic observations with the Webb telescope have begun to reveal these distinct populations, showing that water vapor, methane, and other complex molecules can persist in the atmospheres of some rogue worlds, maintained by a delicate balance of internal heat from radioactive decay and gravitational compression. Perhaps most remarkably, detailed atmospheric models suggest that some rogue planets may maintain surface conditions suitable for liquid water for billions of years, despite receiving no energy from a parent star. These worlds, slightly larger than Earth, could retain thick primordial atmospheres composed primarily of hydrogen and helium that were never stripped away by stellar winds or atmospheric escape. At sufficient pressure, hydrogen behaves as an extraordinarily effective greenhouse gas, trapping heat from the decay of radioactive elements in the planet's interior and creating a runaway warming effect that can maintain temperate surface conditions for up to 8 billion years. The surface pressure on such worlds would be roughly 100 times that of Earth's atmosphere, creating environments where temperature variations are minimal and the sky appears perpetually foggy. Yet liquid water could pool on the surface in vast, stable oceans. Even more intriguing are the subsurface oceans that may exist beneath the frozen surfaces of countless rogue worlds throughout the galaxy. Like a cosmic version of Jupiter's moon Europa, these planets could maintain liquid water oceans sandwiched between their rocky cores and miles-thick ice shells, insulated from the deadly cold of interstellar space by layers of crystalline ice that act as perfect thermal barriers. The physics of these hidden oceans is fascinating. As long as the ice layer remains at least 10 kilometers thick, The combination of internal radioactive heating and the insulating properties of ice can maintain liquid water for geological timescales, creating stable environments where life could potentially evolve and thrive. Recent research has revealed that these subsurface oceans could exist under surprisingly diverse conditions, with planets possessing internal heat flows as low as 1/10 that of Earth, still capable of maintaining liquid water beneath their icy crusts. The formation mechanisms become particularly intriguing at extreme depths when pressure exceeds 200 megapascals, roughly double the pressure at Earth's deepest ocean trenches. The crystalline structure of ice changes dramatically, forming exotic varieties of ice that are denser than liquid water and can sink through the ocean, creating complex layered systems with liquid water sandwiched between different types of ice. These extreme environments could harbor forms of life unlike anything on Earth, adapted to high pressure, eternal darkness, and chemical energy sources derived from rock-water interactions at the ocean floor. The detection of rogue planets requires technological capabilities that push the absolute limits of astronomical observation, relying on events so rare and fleeting that they may occur only once every few million years for any given background star. The gravitational microlensing technique depends on the precise alignment of three objects separated by thousands of light years: the observer on Earth, a foreground rogue planet, and a background star, with the alignment needing to be accurate to within a tiny fraction of an arcsecond. When this cosmic coincidence occurs, the gravity of the intervening rogue planet acts as a lens, bending and focusing the light from the background star, creating multiple, distorted images that blend together to produce a characteristic brightening pattern, lasting anywhere from hours to several months, depending on the mass of the planet and the relative motion of the objects. The precision required for these observations is almost incomprehensible. Astronomers must monitor millions of stars simultaneously, watching for the subtle brightening signature that indicates a rogue planet has drifted across their line of sight to a background star. The light curves produced by these events contain extraordinary amounts of information, encoding not just the presence of the planet, but also its mass, distance, and even whether it possesses moons that remain gravitationally bound despite the violent ejection from their original star system. Advanced computer algorithms analyze these light curves in real time, searching for the characteristic patterns that distinguish planetary microlensing events from the countless other variable phenomena that can cause stars to brighten or dim. The true scope of the rogue planet population will become clear with the launch of NASA's Nancy Grace Roman Space Telescope, scheduled for 2027, which represents a quantum leap in our ability to census these invisible worlds. This revolutionary instrument is predicted to discover approximately 400 Earth-mass rogue planets during its primary mission, providing an unprecedented statistical sample that will finally allow astronomers to determine whether the current estimates of trillions of rogue planets are conservative or if the true population is even larger than current models predict. The telescope's advanced gravitational microlensing capabilities will detect planets with masses as small as Mars, revealing the complete mass spectrum of rogue worlds and potentially discovering populations of smaller planets that current ground-based surveys cannot detect. The Roman telescope surveys, combined with coordinated ground-based observations from facilities like Japan's Prime Telescope and the upcoming Extremely Large Telescope, will enable astronomers to measure the masses and distances of rogue planets with unprecedented accuracy. These coordinated observations from Earth and from Roman's position at the second Lagrange point, 1.5 million kilometers from Earth, will provide the parallax measurements needed to determine not just the existence of these worlds, but their fundamental properties, orbital characteristics, and three-dimensional distribution throughout the galaxy. The data will reveal whether rogue planets cluster in particular regions of the galactic disk, or are uniformly distributed throughout the interstellar medium. The existence of trillions of rogue planets fundamentally alters our understanding of planetary formation efficiency and suggests that the processes creating planets are far more prolific than previously imagined. If Earth-mass rogue planets are indeed 20 times more common than stars, then virtually every stellar system in the galaxy's history has contributed multiple worlds to the interstellar population, implying that planet formation is not just common, but essentially universal around young stars. This has staggering implications for astrobiology, as it suggests that the universe may contain trillions of potentially habitable worlds, many of which could maintain subsurface oceans heated by radioactive decay or retain thick atmospheres capable of sustaining surface water for billions of years. The discovery also fundamentally challenges our models of galactic chemical evolution and the distribution of heavy elements throughout the Milky Way. Rogue planets represent a previously unrecognized reservoir of processed material that has been largely ignored in calculations of the galaxy's chemical inventory. As these worlds travel through the galaxy over billions of years, they redistribute material processed in stellar cores and planetary formation regions, contributing to the chemical homogenization of the galactic disk through mechanisms we are only beginning to understand. Some rogue planets may even contribute material back to the interstellar medium through impacts with asteroids, comets, or other rogue worlds, creating complex cycles of elemental exchange that operate over cosmic timescales. The revelation that rogue planets may outnumber stars by such dramatic margins suggests that the architecture of our galaxy is far more complex and dynamic than the relatively orderly arrangement of stars and their orbiting planets we once envisioned. Instead, the Milky Way emerges as a vast ecosystem where the spaces between stars are filled with wandering worlds, creating a hidden network of planetary objects that connects every corner of the galactic disk in ways we never suspected. These rogue worlds serve as cosmic time capsules, preserving the conditions and compositions of ancient planetary systems while carrying the history of galactic evolution encoded in their atmospheres, surfaces, and internal structures as they journey silently through space. Recent theoretical work suggests that the gravitational interactions between rogue planets and the galactic tide may create previously unknown dynamical structures in the galaxy's architecture, with the collective gravitational influence of trillions of wandering worlds potentially affecting the orbits of stars and the distribution of matter in the galactic disk over cosmic timescales. Computer simulations are beginning to reveal how this vast population of rogue planets might influence the evolution of the galaxy itself, creating subtle but significant perturbations in stellar orbits and potentially affecting the formation of new star systems through gravitational interactions that accumulate over billions of years. The story of rogue planets represents one of the most significant paradigm shifts in modern astronomy, revealing that the universe contains far more worlds than we ever imagined, and that most of these worlds exist not as faithful companions to stars, but as solitary travelers in the vast darkness between stellar systems. As we stand on the threshold of detailed surveys that will catalog thousands of these wandering worlds over the next decade, we face the humbling realization that planets may be among the most abundant objects in the cosmos, with the majority existing in conditions so alien to our earthbound experience that they challenge our most basic assumptions about where and how life might arise and persist. This cosmic revelation invites us to reconsider our place in a universe where planetary worlds vastly outnumber the stars themselves, where life might flourish in hidden oceans beneath miles of ice, or in the exotic atmospheres of worlds that have wandered the galaxy for billions of years, creating a richer, more complex, and infinitely more mysterious cosmos than we ever dared to imagine.